So we've been talking about Newton's first law, and we know that an object in motion will stay in motion and an object at rest will stay at rest. And then it talks about that outside force. So Newton's second law then is where this comes in and talks about that outside force. And when we say outside force, what we really mean is an unbalanced force. And what Newton's law says in words is an unbalanced force results in a change in motion. So that object at rest and that object in a constant motion, that motion is going to change when we apply a force to it. Now in equation form, that is the net force is going to be equal to the mass times the acceleration of the object. It is important to note here it's talking about the net force. There can be all kinds of forces acting on our object, but it's the net force that we're talking about. So net force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second. So let's look at this label a little bit. We have mass, and we have it multiplied by acceleration. So what we get as our label is kilograms meters per second squared. So what we get is kilogram times meters per second squared. Okay, so that's a really messy label, but let's look and see what that's equal to. Kilogram meters per second, our mass times acceleration, is equal to the net force. Force is always measured in newtons. So when we break down the force, what it really means is the mass times the acceleration. That's what a newton is. It's a kilogram meters per second squared. So this is a pretty straightforward problem. We have 650 kilogram car accelerating at 4.0 meters per second squared to the south. What is the net force acting on it? Well, we know the mass and we know the acceleration. So this is a pretty easy one where we just take our equation. Our net force is going to be equal to mass times acceleration. So we're just going to plug in the numbers that we know. And we end up with 2,600 newtons to the south. Now again, remember, this is a vector. Forces are always vectors, so we need to include that direction. Notice that we did not put our label as kilogram meters per second squared. Okay, we just talked about that label, kilogram meters per second squared, being equal to a newton. So we want to make sure that we put newtons if we're talking about forces. So say we have a 5 kilogram block that's being pushed to the right along a frictionless track with a force of 10 newtons. What is its acceleration? In this problem, we know the mass, and we know the applied force. To find acceleration, we would have to rearrange our net force equation into the net force divided by the mass. Well, we know the mass, but we don't know the net force. So this is where a force diagram is going to be really handy, because we do know that we have a 10 Newton force being pushed to the right, but we want to make sure that all of our other forces are accounted for. So we have gravity pulling it down. We have the normal pushing it up, and unless it states it's on a level surface. So this gravity and this normal are going to be balanced. Okay, so there's no motion in the vertical direction. But we do have an applied force over to the right. Since our track is frictionless, we don't have anything opposing that motion. So the only force that we have is the applied force going to the right. So we can say that our net force is equal to our applied force in this situation. So the net force is going to be 10 newtons. So now we can take that 10 newtons and we can plug it into that equation. And we're going to have 10 newtons divided by kilograms, or 5 kilograms, which will give us a positive 2 meters per second squared as our acceleration. Now again, remember, we're not going to write this as a Newton per kilogram. Remember that our Newton breaks down into kilogram meters per second squared, and so those kilograms are going to cancel out. You'll be left with a meters per second squared. So here's an ice cream truck that has a mass of 15 kilograms. It's going to accelerate from rest to a top speed of 12.5 meters per second in 8 seconds. What was the net force acting on the truck? All right, so things we know here. We know the mass. We know the final velocity is 12.5 meters per second. We know the time that it takes to get from there to from rest to there is 8 seconds. And we know the initial velocity was 0. All right, so again, we're trying to find net force, and the equation that we have for net force is mass times acceleration. Well, we know the mass, but we don't know the acceleration. However, we do know the change in velocity, and we know the time it takes to change that velocity. So we can solve for acceleration by what are we going to do? We're going to find the change in velocity and divide it by time. So acceleration is going to be our final velocity minus our initial velocity, and we're going to divide it by time. So 12.5 divided or minus 0 divided by 8 is going to give us 1.5625 meters per second squared. Now we've been talking a lot about rounding lately, okay? And this is actually the middle of the problem, okay? We're not finished with our calculations yet. So we don't want to round just yet. We want to keep this number through our calculations and round at the very end. So we're going to take that acceleration and we're going to multiply it by our mass, and we're going to get 2,343.75 kilogram meters per second squared. Now, there's a couple things that we need to clean up about this because this answer is not a very good one at this point in time. Remember in our rounding that we're going to round to the number of digits that we have in our problem. So 1500 has 4 digits, 12.5 has 3, and time has 8.0. So we can either round to 2, 3, or 4 digits in our answer. Now we're going to go ahead and round it to 4 digits just because that's just a nice number to round it to. So we're going to say positive 2,344 as our net force. And we are also going to change that kilogram meters per second squared to newtons, since we are talking about a force. So here's one that's kind of interesting. We have Stan and Kyle pushing a 75 kilogram sled along a frictionless ice rink. Stan pushes with 55 newtons and Kyle pushes with 45 newtons. And we want to know the sled's acceleration. All right, well, from our problem, we know the mass in kilograms, but we also know that there's a couple forces acting on our sled, but we haven't found the net force yet. So the net force is going to be, we're going to draw a force diagram over here. We're going to have force of gravity and force of normal. Those are going to be balanced because we're not moving in the vertical direction. But we have, who do we have? We have Stan pushing to the right with a force, and we have Kyle pushing to the right with a force. All right, so both of those people are pushing in the same direction. So what we're going to do is we're going to find our net force by adding those two numbers together. So the force from Stan and the force from Kyle, we're going to add together since they're going in the same direction to find a net force of 100 newtons. Now again, we don't have any friction pushing back on it, so that is the only forces acting in our horizontal direction. So our net force is in fact 100 newtons. So now that we know our net force, we can solve for acceleration by taking the net force and dividing it by the mass, and we're going to get 1.333333 newtons per kilogram. Now again, we're going to clean this up. Okay, we have two numbers in every number of our problem, so we're going to round to 1.3, and we're going to get rid of that Newton kilograms and call it meters per second squared.